Okay, so in this video, I'm going to build upon what we just learned in the previous video about model validation and introduce the concept of cross-validation. So before we considered one approach for validation of a model. So now we may ask whether what we did before was the smartest approach for deciding on the choice of hyperparameters. Of course it isn't, otherwise I wouldn't be asking it. So in particular, our model choice, it will depend a lot on the sample that we picked for validation, as we saw before. So we use the validation data set for evaluating the performance of a given model that was estimated on our training data set. So the characteristics of this validation data set, it may matter a lot for which model we pick in the end. So therefore, we want to use as much data as possible for the evaluation of a given model that was fitted on our training data set, so that we minimize the risk of having idiosyncratic noise determine which model that we eventually pick. So in order to do this, we want to consider cross-validation. So how do we get more out of the data? So the fundamental idea in what we're going to see on the next slides is different variations of a holdout method, is that we want to reuse the data in the development data set repeatedly. So basically, what we are going to introduce is a way of testing on all our non-test data, so on our full development data set. So what we're going to do in practice is that we are going to rotate which parts of the data that was used for training and which parts of the data set we are going to use for validation. So how is it that we get the most out of the data? So we get the most out of our data when we use the leave one out cross-validation. So this is the most robust approach. What we're doing with this approach is that for each single observation in the development data, we use the remaining data to train. So we are basically taking our development data, leaving out one observation, then we train the model on the remaining development data, and then we evaluate the performance on this observation that we left out, and then we basically do this for all the observations in our development data set. But this obviously, it makes the number of models equal to the number of observations in our development data set, which is obviously very computationally intensive when we just have a moderate amount of observations in our data set. So what we want to do instead is to use a more general approach called the k-fold method. So this will basically be balancing computing time versus overfitting, which is essentially the whole purpose of model validation. So what we do with the k-fold method is that we split the sample into k even-sized bins, and then for each test bin, lowercase k, we use the remaining data for training. So we use the remaining data for training, and then we evaluate the performance on bin k, and then we basically just rotate our data and use the different bins for training and validation. So the advantages here, they are basically that we use all our development data set for evaluating the performance of a model, and then the training is done with 100 minus 100 over k% of the data. So for instance, if we conducting 10-fold cross-validation, then we're using 90% of our data for training. Okay, so this is basically a visual representation of what we're doing. So it is an example of k-fold cross-validation where k is equal to 10. So what we have here is our training data set, or our development data set. So what we do is that we have 10 iterations because we have k equals 10. And then we have these different 10 folds represented with cubes here. So in the first iteration, we're leaving out this fold, training the model on the remaining folds, and then we are evaluating the performance in this specific fold here. And then in the second iteration, we're leaving out another fold for evaluation of a model and train a model on the rest. And then we get 10 different estimates of errors, right? So we have 10 different iterations with 10 unique subsets of data that we use for evaluation of the performance of our model. And then we basically just aggregate these different errors with a mean to get a total error estimate that we can use in order to select our optimal model. Okay, so how is it that we do this in practice? So what we now want to do is basically to compute a mean square error for every lambda and every fold. So in the example of simple model validation that you saw in the previous video, we basically only loop over different values of lambda, and then we computed then we fitted a model on our training data set and evaluated the performance of the model on our development data set. But the training data set and the development data set, that was not rotated, was not changed at any point in time. So what we now want to do is to loop over both lambdas and different folds. So what I'm going to show in this example here is an example of 10-fold cross-validation. So k-fold cross-validation with k equals 10. So I'm importing k-fold from models selection in scikit-learn, and then I'm specifying that I want 10 splits on my development data. And that's basically what I'm getting here. So this is basically where I'm specifying the different folds in my development data set. Okay, so now what I do here is that first I'm preparing my outer loop, my loop over lambdas. So that's basically a loop similar to what I had in the previous video. I'm creating this list MSE CV that I use for storing the performance of different model for different values of lambda, so different hyperparameters. And then here I'm preparing an inner loop. So here I'm looping over different folds in my data set, so training indices and validation indices that are basically obtained from this exercise up here. And then I'm creating a different list here that I call MCCV underscore, which I use to store the performances of the different the different models that I estimate in these different iterations that I have here. So basically, this container is for these different ones here. Okay. So then in this inner loop, each time I'm creating a new pipeline with the make pipeline. So I create these pipelets of CV, and then I'm using these different alphas, or these different lambda, sorry, and the argument here is called alpha. Okay. So then I specify what in this inner loop, at this point in time, what my training data, what I consider to be my training data set, and what I consider to be my validation data set. That's what I have here. Then I fit a model on my training data set, and then I evaluate the performance on my validation data set, and then I store it in MSE CV. Okay. And then down here, I take this MSE CV and append it with this list of performances on the different folds. And then finally, I convert this MSE CV to a data frame now, where the indices are the different values of lambda. So you can basically imagine what I'm getting now is a data frame called lambda CV, where the indices, they are the different values of lambda. And then I basically have 10 different columns, where each column represents the different mean square errors on given folds, and then for different values of lambda down the rows. And you can basically see an example here. So here I'm just printing the first 3 rows in this lambda CV. So you can basically see this represents, these indices, they represent the different possible values of lambda, only the first 3 in this case, right? And then these different columns here, they represent the performances on the different folds, right? That's what I get here. These are the MSEs for different folds. Okay. And then I store the optimal lambda, so that's the lambda that's associated with the lowest mean square error across the fold. So I'm basically taking the mean over these different folds in order to find the optimal hyperparameter. Then having found my optimal hyperparameter, I now create a new pipeline where I specify that lasso we should use the lambda that is the optimal one. And then I fit I fit this lasso model on my full development data set. So before we had split the development data set into these different folds that we use for training and validation. Now that we have found the optimal lambda, we can use the full development data set for fitting a new model with the optimal hyperparameter, or what we think is the optimal hyperparameter. And now what I'm printing down here is the performances of our 3 different models. We have linear regression is doing much worse than both lasso and lasso with cross validation, but in this specific case, these are basically doing equally well. These 2 different estimates of mean square error, they're not really practically different from each other, right? Okay, but we can also see that it certainly also doesn't do worse than lasso with simple validation, which is nice. So finally, we may ask, what else could we also use cross-validation for? So there are several things. So first of all, we can use it simply just to get more evaluations of our model performance. That's basically just what we saw. We can also cross-validate it at 2 levels. So we can have an outer level, so where we basically make multiple splits of test and development data set. So here I should not have had development, but rather, yeah, okay. We could have different splits of test and development data sets, and then rotate these also, and then the inner loop, then take our development and split it into training and validation, and also rotate these. So we could basically make an additional level of rotation, right? So we could, again, just repeating, we could in the inner loop rotate over different folds in our development data set, but then we can also have an outer loop where we're also rotating what is actually our test data set in our development data set. So this is what we will sometimes call nested k-fold cross validation, which we're going to talk a bit about in the last machine learning module. So that's in the afternoon.